today. So today's agenda is to really study the long-term behavior of 2D Navier-Stokes equation, and following the 2D's next Navier-Stokes equation on the entire space R2 actually. Okay, so the omega in this case is full space, and we know our equation ut minus Laplace mu Laplace u plus u dot delta u plus gradient of the pressure equal to F, where x and t, where the x is from R2 and the t is from 0 to infinity, and it satisfies what you call the divergence free condition, and the initial data is u of 0x equal to u naught of x actually, where the x is in R2. So this is what our Navier-Stokes equation in 2 dimension is full space. So here is the theorem that we are interested in. By the way, we kind of studied in our last discussion, the result that I uploaded, the book that I uploaded basically, the lecture notes that I uploaded based on Roger Timam books. In that, we actually last time outlined the proof of what you call the theorem 3.1 actually. So the theorem 3.1 was about the well-posedness, the existence and the uniqueness of the solution of this Navier-Stokes equation in 2 dimension actually. So we discussed it. And there was also what do you call theorem 3.2 in the same document by Timam that I have uploaded on Moodle. That result talked about the existence of the strong solution of this problem. So what I want to do today. So today's agenda is to prove the following theorems. Okay. So I'll just run through the arguments and provide you some of insights. I'll leave some gaps for you to fill for yourself, and the next thing would be that we would like to study the long-term behavior of the Navier-Stokes equation actually. So here's the theorem that I took. So it says that imagine I have a P that is between 2 to plus infinity, and suppose that the initial data is from space LP, intersection L2 R2, and the initial data is also divergence free. Divergence free, and in this problem the F, what do you call the force per unit volume, or the forcing factor in this Navier-Stokes equation, is assumed, and F is assumed to be L1 on the entire 0 to infinity, with values in LP intersection L2 in R2, and it's also essentially bounded with values in LPR2. Okay, so if we have such kind of an F, then our Navier-Stokes equation, this NSE problem, then this 2D Navier-Stokes equation admits a unique global solution and the global solution U, that U lives in, that U is continuous on the interval 0 to infinity with values in LP intersection N2 R2, and is a square integrable with on the interval 0 to infinity with values in H1 R2. Okay. I mean, if you want to get into the details of what do you call these spaces, please refer to my previous discussion, because in that I have talked about these spaces in detail actually. Okay. So the one thing that makes this different from Tamam's result was that this Tamam's theorem 3.1 was not talking about a global solution actually. Okay, so I would recommend to read the statement of theorem 3.1, 3.2 and compare it with this actually. Okay, so you will see that there is a little bit more in this result actually. So that's about the existence of global solution. Obviously, in order to prove the existence of global solution, most of the work has been done here actually. Okay, so, and we discussed it in detail in the last discussion. So I'll just put myself work on the things which are a bit non-trivial actually. Okay. All right. Now what? Now, if we have, okay, moreover, so this was the existence, moreover, as t goes to infinity, the key part that we are interested in, then the LP norm of the solution goes to 0 as t goes to infinity. Okay, and LP norm. So LP norm, the p can be any number between 2 to infinity. It could be fractional as well actually. So it's not something that is quick proof of this actually. Well, the part of the result that we have done in our previous discussion, I'll just mention it directly and I'll just focus on the things that really I am interested in. As I said, like this is what is the more interesting part that we are interested in actually, okay? That LP norm of the solution to the 2D Navier-Stokes equation goes to 0 in long run. Okay? Let us recall our H in previous case. So the H, you remember, was this collection of those square integrable vector fields which are divergence free. Okay, and V is the H1 intersection H, that is, it's the collection of those vector fields from H1 which are divergence free. And if you remember H1, roughly H1 means that okay, U and the gradient of U are square integrable actually. Okay, this is what really so if u and the gradient of u are in L2, such u's are also going to be in the spaces H1 actually. So I assume that people know about the basics of the Sobolev spaces actually. All right. So what we proved in our previous discussion, we proved that this problem has a unique weak solution actually. In fact, in 3.2 it has a strong solution. Okay. So the key thing that we need to really show is really the globalness actually that we need to focus on. Okay. So we'll try to focus on that. So we showed actually, so if I just give you a brief review, that we showed in our last discussion, or it is well known, that if your initial data is from H and your F is from L1, 0 to infinity with values in L2, then this Navier-Stokes equation admits a unique solution U that is basically 3.1 and 3.2. There exists a unique solution U that is continuous on 0 to infinity with values in H and square integrable on 0 to infinity with values in the domain of what you call A, not domain of A, domain of A1/2 and V. Okay, this is what that we know actually. And there was another thing in the same result that says that the time derivative of the solution U belongs to is integrable on the interval 0 to infinity with values in H minus 1, which is basically V prime actually. Okay, it's really the dual of the V prime. Okay, so the dual of V prime. So this is something that is well known. Along with that, there were at least 4 a priori estimates that we proved for the 2D Navier-Stokes equation. 2 were general, okay, like they are true in any dimension, 2 or 3, and the 2 of them were specifically true in 2 dimension actually. So let me mention briefly those. By the way, for H, I'm gonna use the norm H, okay, simply, and for V, I'm gonna use this norm, this notation. Okay. This notation. So here I'm gonna put H, while for the V, I'm gonna put this notation. Alright, so this is something aside. So we proved some estimates for using Navier-Stokes equation. Let me just give you those estimates quickly. We proved following. Energy estimates. For all t bigger than or equal to 0, we showed that U of t's H norm can be estimated by a constant. We called it previously K1, but you can call it, I can write it explicitly, 0 to infinity plus f of t and mean of 0 to t of 0 to t gradient of u of s square in h norm can be estimated by the norm of u naught plus 0 to infinity f of s h norm ds or dt whatever times 0 to infinity f of s ds in h norm. Okay, so these were the two energy estimates that we proved actually. I mean, if you remember, one energy estimate can simply be obtained by multiplying the Navier-Stokes equation, whether directly or in operator form, with u, and other can be obtained by simply multiplying and integrating. Okay, so multiply the Navier-Stokes equation with u and then integrate over a space variables, and then the other estimates can be obtained by just simply multiplying the Navier-Stokes equation with the ut, the derivative of the u, time derivative of the u, and then integrating with respect to the space variable actually. So we know that. How did we prove it actually? Alright. There will be a result actually, there will be a paper, for proving some of the results. We can't obviously get into the old details, but for seeing some of the minor calculations, I'm going to always refer to this paper actually. By H. Bira, it's on the existence and uniqueness of a strong solution of Navier-Stokes equation. Existence, not well-posedness, but I think it is existence and long-term behavior. Yes. Long-term behavior for the strong solution of Navier-Stokes equation, published in 1987 actually. Okay. So, in the same paper, by Ira that I just showed you, 87. So in this paper actually they proved some of interesting things. So they proved that our problem that we pose in Navier-Stokes equation, okay, in 2D Navier-Stokes equation has a unique local solution actually. As a unique local solution. Okay, so you don't have to worry about the unique local solution. And the trajectories of the solution are continuous over this local interval, over this short interval, or this finite interval, with values in LP intersection H actually. So the key thing that we need to prove to show the global existence actually, we need to just show, okay. So in other words, to show that this solution that is local, valid on a small interval, is also valid on what do you call the entire timeline. Okay, entire timeline. So in other words, to show that u, in other words, the solution is indeed a global solution. Okay, with values in LP as required. What we like to show we can show actually that LP norm of U is uniformly bounded. I mean, if we can kind of show that the LP norm of the solution is uniformly bounded, okay, then it's not difficult to deduce that your U is also a global solution actually. Okay. So to show the globalness, we have to kindly just focus on that this guy is uniformly bounded actually. So what if you have these uniform estimates, okay, then you can deduce then your solution is going to be the global solution. Okay. So for this, I'm gonna use what you call so-called the Gagliardo-Nirenberg inequality. Okay. So let us start. So what I'm showing is the uniform boundedness, so that I can say that my solution is a global solution actually. Okay. This is what the key. So I'm going to start with Gagliardo, following version of the Gagliardo-Nirenberg inequality. Okay. So you can find the Gagliardo-Nirenberg inequality in the first chapter. Okay, and Gagliardo-Nirenberg inequality. Following version of Gagliardo-Nirenberg inequality that says that the LP norm of U can be estimated by C times the gradient of norm of U in H norm with the power P minus 2 upon P, and U is going to be 2 over P. Okay. Where C is some positive constant. So it's some positive constant. I mean, you can take your generic Gagliardo-Nirenberg inequality, you will see different symbols in it. So if you so your Gagliardo-Nirenberg inequality in general looks like this actually. So dj u, okay, roughly. So I'm just writing a rough. I'm writing, say, a rough. So I think it goes something like this. dj u in LP norm, jth derivative, LP norm of the jth derivative of the u can be estimated by the nth derivative of u with LQ plus times norm of u with LR and some powers alpha and 1 minus alpha, where this G, J, P, M and alpha and 1 minus alpha, they satisfy, I think, some equation actually which I don't have actually in the mind actually, but you can see it from the book and you can deduce. So to make this into the so to deduce what do you call our equation, the inequality that we are interested in, that goes like the LP norm of the U can be is less than or equal to the gradient of U L2, okay, because our H is L2, times P minus 2 upon P, yes, I think it was P minus 2 upon P times U and LR, okay, L2. So this means to get an inequality of this form, what you need to take J equal to 0, M equal to 1, okay, alpha equal to P minus 2 upon P, and your Q and R should be 2 actually, okay. So using these values and using the abstract version of Gagliardo-Nirenberg inequality, you can deduce the inequality that you want actually, okay. So I'm just giving you a rough way of doing it actually. So what you have to do, you have to go back to the chapter 1 of the book and see that or think for yourself that how using the abstract Gagliardo, the general Gagliardo-Nirenberg inequality, you can deduce this out. Okay, so how this can, and obviously, the dimension in this case is also 2, so n is 2 actually. Okay, so by general Gagliardo-Nirenberg inequality, you can deduce this particular Gagliardo-Nirenberg inequality, which will be helpful for us. Okay, we both have in H. Now, what can we do? Now, if I do this, so the LP norm can be estimated by this and by the gradient of U in H norm and U in H norm actually. And interestingly, for U in H norm and gradient of U in H norm, we have these estimates actually. Okay, so you have control over this side actually. Okay, because you are U naught and F, you have assumptions and they have, what do you call, they are behaving nicely. Okay, so for U and the gradient of UH square, you have estimates. So what we can do actually is that if you take say Q equal to P over P minus 2 and compute the integral from 0 to infinity of norm of U in LP raised to Q dt, then obviously I can estimate this guy by constant time 0 to infinity, and integral of gradient of U in H norm P minus 2 upon P and everything power. So it's like, okay, take the power Q on both sides and then integrate. So you're going to get, what do you call Q? Q is P power P minus 2 times U H P upon 2 power P over P minus 2